the recording then and welcome everyone back for the last hurrah. We have 2 more weeks of classes to make it through and then finals week. Anyone else here run track in high school? A couple folks. So I ran long distance track, which meant I had to go around the track many times. And I always waited for the bell, right? When you start your last lap, they ring the bell. That's what I'm hearing in my head right now. Like the bell is going, doesn't mean we're done, but it means the end is in sight. And we just got to hang on for another lap. How's that for an analogy? It works. Even if you didn't run track, I'm guessing that you at some point watched a track race in which you witnessed the bell being rung and the moment of glory that is. So first things first, we got Mr. Bladimir here to lead us in our formative assessment number 6. Not quite the last one, but the second to last one. So come on over here. Let me make sure that you're in the frame here, Mr. Tall Person.
Hi everyone on Zoom.
There you go.
Thank you, Lisa.
Thank you.
Hey people. Yes, that's great. Hi people in the classroom. I hope you are doing well. I hope you had a good Thanksgiving break. I hope you enjoyed that week. Personally, I think that was shorter than I wanted and shorter than I needed. It was like just a weekend. But it was good to have one. Better than none. Today, we will be discussing the 4 questions that were included in our formative assessment 6. As Lisa said, this is not the last one, but we are almost there. So I read all of your answers. They were pretty good, so thank you for your time. And I think that question 3 especially was something not complicated, but maybe tricky. So for every question, I have some kind of main idea or highlights. So I will share that and we can discuss your answers for every question, okay? So if you have additional questions at any time, just raise your hand and we can talk about any of these details and ideas here. Let's go with question 1. So, yes, they are looking at the screen, right? Yes. Thank you. So question 1, why is it important to establish the best fitting unconditional model for time before examining predictors of interest? Why do you think that's important? And I read an answer that was like, because that's what we should do. And I say, yeah, that's something that we should do, explore time. But why, more specifically? Why do you think that's important? Yes, it's related to the variation in the outcome at level 1 and level 2, for example, related to time. Yes, the idea of variance. Do you have more ideas about that? Ideas related to time, variance, the model we have at that point without level 2 predictors?
I'm thinking that would be like a baseline model, so we can
Yes.
adding like a time invariant predictor. How would this be helpful?
Exactly. Yeah, it is. It is our baseline model. And when I was discussing this with Lisa, to me, the main focus was on the fixed effects. But then when I talked with Lisa, I realized, as Kendall mentioned, that the idea of the variances, the sources of variance, are very important. So that's why you will see here, this is the slides, the set of slides that I prepared. Because as I told you, without slides, it's like not formal. Don't ask me why. That's in my mind. So, if you go to lectures 7A, slide 13, you will find like a summary of the main ideas for this question. So, on the one hand, we have the fixed effects. We have the shape of time, for example, because we know that time can have different shapes. Can be linear, non-linear. Can be continuous, non-continuous. That's one thing. The other is about the variances that we have, the random effects, because those things are the individual differences that the level 2 predictors will be explaining. Yep. Now, I'm using quote for explaining because that's a difficult word. Explain something. To me, it's like hard to define sometimes because we can find relationships, but it doesn't mean that something is causing the other thing. To me, explaining something is related to the idea of something causing something. Sometimes it's not the case. That's a hard word to me, but maybe it's not the case for you. So those sources of variances are the thing that we will be trying to explain with our level 2 predictors. Because, and I read this in one of your answers, people things can help us explain people differences. I think that that's a good summary. So as you can see here, this idea of level 2 predictors moderating the effects of time is something that we will see in question 4 again. Because once we have time, the fixed effect of time, we can use our level 2 predictors to explain part of the individual differences in the fixed effect that's across level interaction. So the level 2 predictors will help us to moderate time. So the reference model, the baseline model, is pretty important. Now, the other thing is, based on our baseline model, we can then determine how much has been explained, how much of those individual differences in time or at baseline or at time zero have been explained. So that's the relevance or importance of setting our baseline model well. Additional questions? Is that clear? People nodding? People on Zoom? Okay, thank you for your feedback. If something is not clear, just ask questions, please. So let's go to question 2. Vocabulary question here. List as many synonyms as you can think of for a level 2 predictor in longitudinal designs of occasions nested in persons. So, can you help me with this one? Level 2 predictors can be named. Sorry? That's level 1. Within, yes. The opposite. Between person, yes, exactly. Macro, yes. That's something that we talk. I mentioned that when we were talking with Lisa. In this context, in the longitudinal context, macro is not used often for some reason.
But there's no reason you couldn't use it.
Exactly.
It goes with level 2.
Exactly. Yeah. So that's a good one. We have between macro, person level predictors. Exactly. Yes. Inter-individual things. Exactly. Alex?
There are things that won't change across the study.
Time invariant? Time invariant things. Yes. And I think that we cover most of them. So here I selected some because we have individual person or people, variables, attributes, or characteristics. They are also known as time invariant things, between person things, or inter-individual things. So I think that was a easy question. Do you have any other? Time invariant. Yes, Taylor, thank you. I think that I read something like substantive predictor. And I was looking for that, but I couldn't track the origin of that one.
I know where that one came from. So yeah, there were a couple of comments about substantive predictors versus controls. Like those are interpretational distinctions. I'm
Yeah.
more concerned about at what level of sampling the predictor is measured. And these are people things that have been measured once. That's the
Yes.
idea. Whether you think
Ah.
it's a control variable or something your thesis is all about is up to you.
Great. Thank you. So yes, I didn't know that the substantive predictors were related to the idea of control and substantive things.
Yeah, it's a contrast.
Oh.
Like some things go in the model because someone else cares, and some things go in the model because you care.
Ah, okay. Thank you. Thank you for that. So let's go to question 3. The tricky one. Yeah, this is a good one because question 3 says, how do multi-level models, as estimated in SAS mix, data mix, or Elmer in R, handle missing predictor data? And I know that handle is a word that Lisa doesn't like. I like it. To me, it makes sense. But how do multi-level models handle missing predictor data? They deleted.
That's it.
Exactly. Now, I think that we had a lot of dispersion here. I read some answers linking this to the use of full information maximum likelihood, for example, or that we could include predictors in the joint log in the joint likelihood in our models. Those things are related, maybe, but the main point of this was here. If you go to slide 6 in lecture 7b, you will see an example that we covered in our last class, if I'm not wrong. This one here. So in the models that we have seen so far, cases or subjects with some missing data, they are not dropped entirely. However, the model is using complete cases for rows. So the model is performing listwise deletion for those rows with incomplete data. So for example, as Lisa explains here, if we have a model with time pred, and person pred to predict our dependent variable, we would be including rows 1 to 3 only, these ones. Because the other rows have missing data. So now, yesterday I was thinking, and I have a question, Lisa.
Yeah.
So here, for example, we have a model with time, just time, right? And we are not including row 7 in the dependent variable, right? So why?
Because every row that's incomplete gets deleted.
Ah.
It doesn't care what the role of the variable is.
And that's different to the assumption of MIR, right?
The assumption is that what's left for that person is a representative sample of like what you would have had if you had all their data.
Awesome. Yes. So even if you have missing data in your dependent variable, that will be deleted in your analysis. That's what we have. And that's important because when we assess relative model fit, the measures we use, the likelihood ratio test, is based in the model log likelihood, which is based on the sample, on the number of individuals we have or the number of occasions. Whatever the sample size is should be consistent between comparing models. That's why this is important. Questions? Yes?
On your earlier slide that you had up, on like the actual answer for this,
Yep.
you had something about assumptions. So there's no assumptions for predictors, it's just if they're gone, they're gone.
They're gone.
Yep.
MCAR. Missing completely at random.
Yes, good point. The assumptions, for example, the MIR, that's applied to the outcomes, not to the predictors. The predictors are deleted. It's just like MCIR, missing completely at random. Yes, good question. Anything else? People on Zoom, are you right? Good? Thank you. Thank you for your feedback. So that means that we can go to our last question here. Question 4. In growth curve models, what roles do level 2 predictors play in the model for the means? What kind of fixed effects can they have? What do you think? Any ideas? What can we do with those level 2 predictors? Their main fixed effects or their interactions? What do you think?
It's been so long since I thought about this. So I think, like, I do not even remember what I wrote. But they're interactions, aren't they?
Yeah.
That's one of them.
Yes, exactly. And that's related to the idea to the idea of moderation. Because when we have interactions in our model, we are saying that whatever the main fixed effect of time now is being moderated by this level 2 attribute. So we can see how the fixed effect changes or varies depending on people attributes. And that can help us to explain part of the individual differences around the level 1 effect, not fixed effect. I didn't say that because yesterday we were talking with Lisa about this. And yes, one of them is interactions. Now, before talking about this, what's the role of the main effect of a level 2 predictor? Why the level 2 predictor should be there?
Does it take away some of the variance? Like it partitions the variance a little bit more because it's systematically varying, not randomly.
Oh, that's one type of fixed effect for level 2 predictors, systematically varying fixed effects. But yes, yes. Actually, we have 4 kind of fixed effects here. We will be covering 2 here. One of them is cross-level interactions. The other is what I'm asking for, and the other 2 will be covered in this class, I think, today. So, what about the main effect of level 2 predictors in our model? What are they doing if they are not moderating time? Because that's what the cross-level interaction is doing. What's the main effect of a level 2 predictor doing in our model?
Explain differences in the slope and intercept.
Oh, well, the slope, that's the cross-level interaction. But in the intercept, yes. Yes, that's what the level 2 predictor will be doing. Will help us to understand or to explain part of the individual differences in the mean outcome at time 0. That's what the main effect is doing. And that's why the main effect at level 2 will reduce part of the random intercept variance. And the cross-level interaction can help us to reduce part of the random slope variance of the level 1 predictor, because it's helping us in the second case. The cross-level interaction is helping us to understand why some people have or need different slopes for the level 1 predictor. Okay, so in general terms, I think that level 2 predictors adjust the growth curve when we are focused on change, or they can help us to adjust the mean level of the outcome when we are focused on fluctuation over time. Now, if we want to talk about details, we know that the main effect can help us to explain part of the individual differences in the mean outcome at time 0, which is related to the intercept in our model, and the cross-level interactions can help us to understand part of the individual differences in the effect of a level 1 predictor. Yep. And today we will cover the other 2 type of fixed effects. So, questions? Was it hard? What do you think? Yes. Yeah, no. Especially after 1 week without talking about these things. So, I hope you enjoyed this discussion. If you have any additional questions, you can email me and we can discuss now in class the other things that are not clear yet, okay? Thank you. Thank you.
And yes, that was a long time ago. I agree. But the good news is that hearing it the second time, it'd be easier than hearing it for the first time. So that's a well-known learning result, I think. Don't know. There's probably a name for it, but I don't remember what it is. All right, let me make sure I'm still recording here. I'm always nervous about that. Okay, looks like everything's still cool. All right, so yes, couple of things. So just to reiterate, the best fitting unconditional model tells us not only how much variance we have due to person differences, but what kind. So for instance, if you test random slopes for time and they're not significant, that means you don't have a lot of individual differences in change to predict, and trying to fit cross-level interactions between a person predictor and time is probably not going to go well. Like there's not a lot of signal there for you to be able to see those effects. Now there are certain situations in which that may be a reasonable thing to do, and we'll talk about that today. But this is the main idea. It's like the model for change dictates what kinds of individual differences there are, and therefore what roles your time invariant predictors have to play. The same thing would be true with respect to other level 1 predictors. So we've only had time and things related to time in there, but anything that's measured at each occasion is a level 1 predictor. Those can also have random slopes across people. So the extent to which stress impacts your mental health, for instance, that relationship may vary person to person, and moderators of that could be person level characteristics. So it's a more general concept beyond time. Yes, question?
So, in that case, would you have to, so if you had another level 1 predictor, is that's not the same as like partitioning the variance? Like that variance is still part of time, or is it? Like, I'm trying to think like, okay, so for time, we put in all the effort to like understand what the pattern is over time. Like, would we have to do that with another variable as well, and like have multiple matrices and like?
Yes. So let me repeat the question. So time is special because that is the most prominent design characteristic of most longitudinal studies. Like that is the point, is to watch time and to watch change over time. There are other kinds of studies in which time is somewhat irrelevant. So fluctuation kinds of studies where you're looking at things that are transient, stress and health and social support and all those kinds of things. But the question was, so we made this big deal out of making sure we understand everything related to time and all the sources of individual differences related to time. Should we do that for every level 1 predictor? And yeah, kinda. But I would not expect necessarily all of them to contain individual differences in that effect. The way that time is, it's just a much more salient design characteristic. And you're right that, for instance, if I have stress relating to mental health and that has a random slope, then what I'm also saying is that the variability in the outcome differs as a function of within person stress. So that's a quadratic variance function along that variable too. So your V matrix just got 3-dimensional, I think. Like there'd be time and stress in a box, and at that point I'm out of elbows to make it work, but you get the picture. Yes. So yes, level 2 predictors can be things you care about or things you don't. They can also be categorical things, continuous things, or somewhere in between. Any kind of predictor at any kind of level is cool. We can all agree that deleting cases that have missing data is probably not optimal. To fix it, that's next semester, either in my class or in the missing data class, because it requires multivariate analyses in which your predictors essentially become outcomes that are also being solved for by the model. So just wanted to say a few things about that. Any other questions or things you want to review? I know it's been a minute. I'm not expecting you to have perfect recall of everything that has happened this semester, trust me. I don't even know what happened this semester, and I was theoretically in charge, so I'm right there with you. In terms of what is remaining, so we have one more formative assessment, but I'm making it due next Wednesday instead of next Monday because it is 2 story problems that I'd like to spend a good deal of time going over in class. Bladimir, you are off the hook because these are story problems from my previous research in which I already have the answers all queued up, and I don't want you to have to do that when you have your own other work to do. And more stories if we have time, so a few other things. Because what I'd hope for you to be able to get out of this is not just the nitty-gritty of how to actually estimate these models, but like, if I'm faced with the situation, like, where do I start? Like, how do I think about what kind of model, what are the important issues, what do I need to pay attention to? Like, that's the stuff I want you to take with you. Because once you figure out where you are in the landscape of these models, then it's a lot easier to go back to your notes, to go back to the book chapters, to go back to your resources and figure out the nitty-gritty part. So that's what I'd hope to end with, is a bigger picture understanding of what's going on. Umbrella, that's what I'm doing here. This is an umbrella. Let's see, your last homework will be due on Thursday of finals week. I hope to open that by Thursday, I think, so you'll have 2 weeks to work on it. And yes, it is easier than the last one, I promise. The last homework is essentially adding 2 time invariant predictors to homework 3. So that's the story. And then that's it. So I will be planning on having my regular office hours on Monday and Wednesday of finals week, as well as office hours during the time I would normally be teaching, 12:30 to 3:30. So you can get a hold of me any of those 4 days. But after Thursday, I'm going to wake up Friday morning, turn in grades, and get on an airplane. That is my plan. So if I can be as transparent as possible, that is what is happening. And at that point, whatever grade you have earned will be turned in. And if I screw something up, I'm happy to make changes to that after break. They always allow us, after about a 2-week period, an entry into changing grades if something happens. So, any questions on outstanding work or stories or any of that stuff? No. Okay. Well then, bye-bye webpage. Bye-bye yellow slides. Thank you, Bladimir. Different yellow slides. All right. Let me see here. Let's talk about some review, shall we? Would that be good? Okay. Let me start with this idea of, let's go slide 16. This is lecture 7B, we're in here. So the big picture, what level 2 predictors are for, in growth curve models in particular, is to moderate the growth parameters. And so this requires gestures and words. So the main effect of a level 2 predictor moderates the intercept. This is the accompanying gesture. Makes y, predicted y, go up and down. It is y at time 0 specifically in these models. If the if the predictor also interacts with time, then that is creating different linear slopes. And if I have a quadratic time slope and I have an interaction with time squared, that is creating different quadratic time slopes. So to put those all in an equation would look like this. So because there are 3 kinds of u's, and what are u's called, by the way? If you're writing in a paper, you can't call them u's. I heard it. Starts with an R. Louder, I hear it. Random, there we go. Yes, so this is the idea that there is a random effect variance across persons in the model. U0I is the specific random effect deviation for this person. So U0I is a value, how far off this person's predicted intercept is from the one that they would have had. And so to the extent that education, for instance, matters in predicting this outcome, the U0I variance across people should be smaller than it was before. So I know, Bladimir, you said you don't like explain. I agree with you in the sense that this is not a causal relationship. I agree with you in that sense. But all I'm talking about is there is this much variability before and now there's less. So whatever words you want to use to go with that idea is fine by me. That is a common misconception, by the way, that some folks like to say that if you have longitudinal data, that gives you causal inference automatically. It does not. Just because you measured someone repeatedly doing whatever they're doing in their life without you doing anything to intervene does not give you causal inference. I think that there is a stronger possibility of causal inference in longitudinal data because you can control for person constant things and watch what happens within persons, but that doesn't get you all the way to that. So I don't ever get that chance in my work. Gamma 1, here, this thing is a cross-level interaction in particular. So that means between a level 2 variable and a level 1 variable. In this example, education is level 2, person level, and time is level 1. And then we can do the same thing for quadratic time. So then we would have 3 potential pseudo R-squares to talk about as effect size in this model. We can also talk about total R-square. Do you remember that? Those words sound familiar at least? Pseudo R-square versus total R-square? So pseudo is the idea of per variance component, or per pile, as I like to say. Like, of the intercept variance, how much did the main effect of education get? Of the linear time slope variance, how much did the education by time interaction get? Of the quadratic time slope variance, how much did the interaction of ed by time squared get? Those are pseudo R-squares. Likewise, when we initially added time and time squared to the model, we can talk about how much the level 1 residual variance was reduced by these fixed effects of time. If we had other time varying predictors, like stress at each occasion, that would go in here as well. That would be a beta 3, and then I would have another beta 3 equation falling off my slide here. So as many betas as you have in your level 1 model, that eventually will contain fixed and random effects, they get to become outcomes at level 2. Okay, total R-square then, what's that? I'll take gestures, all of it. Yes, Total R-square is, okay, my head hurts. I can't keep track of all these different R-squares. How much outcome variance did you get? Period. That's total R-square. And that is computed by taking the y hat that is predicted by your fixed effects only, putting it in a data set, correlating it with the real one, and squaring that correlation. That is the same way it is computed in standard linear regression, and it has the same interpretation. So I think of it as a complementary effect size because it's a more global assessment of how effective your model is at predicting some outcome, whereas these are much more specific. Okay, how we doing? So this is all nice and tidy right here, right? Like if you put the predictor in this level 2 model, it explains its U variance that goes with it. If you put a predictor in the level 1 model, it explains the E variance. Nice and tidy. Do you know where I'm going with this? I'm going to break it. Yeah, nice and tidy is not the general rule, I would say. No. But here's what this looks like in composite form. So if you take out the beta placeholders and substitute in what they stand for, I have parentheses here to show you what that looks like. You can see more readily how gamma 1,1 and 2,1 are interaction terms of education by time and time squared. Here is the SEM version of that. We talked about that briefly. That's coming next semester. Don't need to spend too much time. Here's the multi-level SEM version of that. And here's some new stuff. Okay, so the role of time invariant predictors, as we've discussed at length, is to answer the question, why do some people change differently than others? Why do some people have higher predicted values at time 0? Why do some people change linearly, quadratically, piecewisely, if that's a word, whatever type of time function you have? Each type of time function can have individual differences. So we can talk very readily about how the main effect of education, gamma O1, reduces this variance, this interaction reduces that one, and so on. And here's our handy-dandy pseudo R-square formula. So here's a question. And this is a question that does not have a single right answer. It's still somewhat controversial in the field of multi-level modeling. What if you don't have random effects? So let's say that you have a study in which you test random intercept, random linear slope, random quadratic slope, and you don't find them. But your research question is all about how education moderates change over time. The fact that you don't have random effects here, does that mean you're done and that you can't answer the question? My instinct would be like, no, just watch. But some folks would say, no, you're done. The logic here is that if a level 1 effect, so a slope that is a within-person relationship, does not vary randomly over people, so there's no random slope variance that was significant that you detected, then it doesn't have any variance for that cross-level interaction to predict. If people don't change differently, end of story. That's the logic. Doesn't make sense to say, do they not change differently because of this, or this, or this? Different is done. And research has shown that if you fit a model that looks like this, without the corresponding random slopes that go with these cross-level interactions, and they should be there, these are all wrong. Their standard errors will be too small, their p-values will be too small, because part of the variability in what they're predicting is not represented in the model. Random slopes add to the variability in the sampling estimates of these things. So that's one perspective. The alternative perspective, which is where I fall, is, well, yeah, it doesn't mean you're done, it just means you need to be careful. The power to detect random effects is often lower than the power to detect fixed effects, so you could be making a type 2 error. There could be random slope variance there, you just didn't find it. So from that perspective, it still makes sense to go ahead and fit cross-level interactions, but with some caveats. You would never ever want to start here. You would always want to check to make sure that the random slope variances, whether they need to be there or not. Because if they do need to be there and you don't have them, that's going to be wrong. If it looks like they don't need to be there, then you just need to be a little bit careful, but I think you can go ahead and proceed. So let me give you a concrete example and introduce you to a new vocabulary term called systematically or non-randomly varying. And yes, if fixed is red and random is blue, then this is purple because it is a hybrid. So, in a nutshell, if you think of a continuum of how effects vary across persons, fixed means everybody gets the same. Like the slope is 4, the end, fixed. Random means everybody gets their own. The mean is 4, but you can have a U and you can have a U, and it's fine. Systematically varying is in the middle. It means that it's not the same for everybody, and it doesn't vary individually. It varies systematically or deterministically as a function of some predictor, but not otherwise. That's what that would mean. So as an example, let's say that you're fitting a model in which you're examining individual differences in the effect of time, and that random time slope was not significant. Let's say that you espouse my same viewpoint and you're like, well, I'm still going to go ahead and answer my research question, and you find a group by time effect that is non-significant. Okay, well, the time slope doesn't vary randomly across people. It looks like the time slope is not moderated by group. Then I would say the time slope is fixed. Everybody gets the same, and that's sufficient from what I know so far. However, if I were to fit the group by time interaction and find it to be significant, that is where I would use the term systematically varying to describe the slope for time. It's not that everybody needs their own, it's that the treatment group needs one and the control group needs another. But within groups, everybody is the same. Or people who have this level of education get this slope. If you have 2 years less, you get this one, you get this one, you get this one. So it could be moderated by a continuous variable or a categorical variable, but the idea is that it doesn't vary beyond that. Okay, is that clear? Okay. So systematically varying as kind of a hybrid midpoint between fixed and random. Second scenario here. Let's say that you fit your growth model. You find a significant random time slope. Hooray, you have individual differences in change to go and predict. If the group by time effect is significant, then we would say it's systematically varying. But what if at that point the random time slope disappears? It goes to 0, or it goes to something very close to 0, and you do a likelihood ratio test, and it doesn't hurt the model to take it out. That can happen. Now, in this context, I would still say that the effect of time is systematically varying if you no longer have a random time slope to go with it. But my question for you is this good news or bad news, do you think? From a, I want my research hypothesis to be supportive perspective. What do we think? Zoomers, you're being quiet today. Roomers are quiet too, to be fair. But is it good news or bad news?
Does it mean that group matters more than time?
Group matters. I wouldn't say that it matters more than time because they're not in the same competition. The fixed effects of time are targeting the level 1 residual variance. The effects of group would be targeting the random effect variances that go in that level 2 model. What do we think? Is this a good news result that you included this interaction and then the random time slope went to 0? Question from the Zoomers, it depends on if you think all the differences are a predictor. Is that a good thing? Otherwise, it is bad. Think of it from an R-square perspective. If I had random slope variance and I put a predictor in to explain it and it went away, said differently, my slope, pseudo R-square, would be 100%, be 1. Is that a good news or bad news? Yeah, you explained everything. And by everything, I mean all the reasons why some people grew faster than others. It was because of the group they were in, and that's it. There are no more reasons after that. That's what that would mean. So I think it would be good news. However, reviewer 3 is going to be all over you because they will probably point out that you didn't have that much individual variation to begin with, and so therefore it's really easy to get it all when you barely have any. And then you'd have to argue based on some kind of measure of effect size for slope variance that you have something worth talking about. And that gets a little squishy, shall we say. So the idea here is that you had individual differences in change. You put in group by time as a way to explain them, and they went away. All of them, or nearly all of them. And that would not happen if the group by time interaction was not a sizable contribution to the prediction. And if you had a random time slope to begin with, and it's still there after you put in your predictor, in both cases I would describe the effect of time as random, meaning that everybody needed their own to start with, and even after you let each group have their own time slope, they still need their own. So there's still other reasons why people change differently from each other that are not part of your model yet. That's what that would mean. So level 1 predictors can be fixed, random, or systematically varying. Level 2 predictors can only be fixed or systematically varying. They can't be random over a higher level yet. But if you have one, then they can. But that's not this class. Okay. I'm looking at your faces. I'm looking at the Zoomers' faces, and I'm seeing a whole lot of make it stop. Okay. How can I help? Yes.
So that middle box, it's open. You're explaining away person level differences, not which is assumedly what we're not interested in studying for this project, for whatever project you're doing a longitudinal.
So I am assuming that you are interested in explaining why some people, let's say, improve more readily than others. So.
Then you're explaining away essentially everything and why those people differ. And that is not a bad thing.
See, I think it's a good thing if you want to be able to say definitively, here is why you're going to improve more than someone else. It has to do with you're in this treatment group or not this treatment group. Or it has to do with these 3 characteristics that you walked in the door with.
And not the actual intervention.
Well, so in this context, I pick group because it's an easy example. Because then you can think about the control group has one slope, the treatment group has another slope. Within those groups, they're homogeneous, though. That's the key idea. There's no more random individual variation beyond what is already implied by group or any other level 2 moderator. Oh, there, I stumbled onto something useful, I think. Good. Yes, you then you.
Sorry. Can I think about that from like somewhat clustering perspective, that this effect is at the clustering of group level instead of the lower inversion level?
Question was, can we think of this as the effect is at the clustering level rather than the lower level? I'm not sure you can think of it that way, or maybe I don't understand what you're trying to say. Can you keep talking, please?
So it's like, for example, if it's not a treatment or random group, it's like, for example, if you're in this classroom or that classroom or a certain classroom,
Mm-hmm.
and the effect of time interacting with your classroom instead of with individual or each student underneath that classroom.
Are you talking about a 3-level model of occasions within persons within clusters? Okay, so that is not my story. But if I try to answer that, the same logic would apply. Clusters could differ in how their people change. And so like if you assign, a cluster to a control arm or a treatment arm, and there's no more cluster differences, then the interpretation would be the same. That your assignment to a group is why the clusters look like they change differently. Same idea. Yep. Okay.
I'm trying to interpret this in like really plain language, and my interpretation is probably way off. But if we take that box with the ... if random time was initially significant, it's not significant after the interaction of group and time. Could we describe that by saying this situation in real life is probably really, really rare?
Yeah,
Usually
rare or can't happen.
individuals contribute variance in addition to their group membership. So it could mean either that your group predictor was just weirdly really significant, like you're comparing 2 classrooms of children and one group had like a bunch of Halloween candy right before class started and the other group had none, and like the Halloween candy was the only thing that created the differences between the two groups. And so you can say you found a really huge effect of this thing. Or, like, reviewer 3 is probably going to say, probably it's not that your predictor was super weirdly, predictive. Probably there's something wrong in your data set. So maybe you gave a test to 2 different groups, and one of them there was a ceiling effect, or there was a floor effect, or like you set it up wrong, or you didn't consider something. Like, it's very rare in real life for one time invariant predictor to explain all of the variance between things. So it's going to make your data look suspect.
So I think I understand what you're saying, and to me, that idea does not go into this box. Because this box is, you had individual differences in change, you tried to explain them, it didn't seem to work because that interaction is not significant, but nevertheless, your individual differences in change went away. That would not happen beyond like just sort of like a little bit of, like, it would have to be like a marginal result in both cases to make that happen. Like this box theoretically isn't really possible. I think what you're talking about is potentially adding in like one predictor that is kind of a Trojan horse for another idea, which would be like a confound.
Like a proxy.
Yeah, like if group wasn't randomly assigned and you found a whole bunch of other variables that differed by group, then you can't really say it's group doing the work here, because group is a proxy for 8 other things. And that would be indeed something reviewer 3 could complain about. And why we randomly assign people to groups if we possibly can. Okay, so point of the story here. If you're in this situation, like NIH gave you $1 million to cure cancer, you did some sort of study, you found that differences in the rate of improvement in cancer did not exist, like your people all changed the same, but you were going to then test moderators of change, NIH is not going to want to hear that you can't do that analysis just because of the way the results turned out. So I think that you can, but the trick is make sure you don't need these first as one thing, because that will lead to higher type 1 error rates if you're wrong. So we always test the random slopes whose variances are to be explained by the cross-level interaction terms first. That's the one thing. The other is to watch out for type 1 error. So, or type 2 error, excuse me. So this is a paper that went through multiple rounds of review, ultimately was rejected, and I haven't had the strength to go back and resuscitate it yet. But I have the conclusions from it. So yes, any of you who feel bad about projects that are languishing in your folders, hi. Nice to meet you. Let me show you the graveyard that is my folder directory of papers and ideas and things. It happens. But someday, this will be in print somewhere, even if it's just a psych archive server. I can just stick it on there and it'll be fine. So this was the question that I wanted to answer. It's like, well, how do you solve this problem of type 2 errors leading to you to say, oh, I don't need the random slope, but then it turns out you actually do? Well, slope reliability. In the same way that rather in small samples, we might be more concerned with providing effect size, not just significance levels, the same thing would apply to these. So in a simulation study that we worked on, I found in the results that essentially if you come up with a criterion of keeping your slope variance that's not based on significance, but instead is based on slope reliability, that actually works to solve the problem. So I came up with arbitrary cutoffs of slope reliability of greater than 0.2 if you're using REML, or 0.15 if you're using ML. And if you adopt these cutoffs in conjunction with the likelihood ratio test, then the type 1 error rate was acceptable. So that's an informal recommendation that I would provide. As a point of review, though, why do you think we might need different cutoffs using REML versus using ML? Why would that matter? These are different methods of estimation for this model that would be otherwise equivalent and have the same numbers of parameters. These are differently constructed likelihood functions. That is so the effect of this difference on the standard error is a consequence of the problem, but I wouldn't say it is the problem.
Different sample size.
Yeah, what did you say, Erica? Small sample sizes, yeah, like, so the sample sizes I looked at here were 10 to 50. So I'm trying to break the model, essentially. So as we talk about in conducting simulation research, you can see how well things work under suboptimal conditions. I'm trying to make it suboptimal. So in smaller samples, what happens to your random effect variances if you're using maximum likelihood? They're too small. So they're underestimated, which means you would have lower reliability, and thus potentially a different cutoff would be needed to compensate for that. So that's why I landed on these particular values for this. So those are the two things I would recommend when you're in this situation. Make sure that you don't need your random slope variance with the likelihood ratio test. And if you're dealing with a small sample and you're concerned about type 2 errors, maybe look at slope reliability and keep it anyway. All right, so here is an example with group throwing in here just to show you multiple predictors. So if I add in gamma O2, what is that in English? What's this thing doing right here? It's modifying the intercept. What would it look like if I wrote it in code? Is this a main effect or an interaction term? This one, gamma O2. This is the main effective group because it's moderating the intercept. The interactions with time would be group gamma 1, 2 and 2, 2. Yep. And so if I add the main effective group, the random intercept variance should go down. If I add the cross-level interactions, the corresponding slope variances would go down. So I want to do this with a little demonstration, and I apologize that the slide version of this is not nearly as exciting, but this is meant to be an active demonstration. Okay. So we have, let me see here. Yep, there we go. This one is, actually, I built this into the slides. The active one is a few slides from here. I got too excited. Okay, so starting off with an empty model. Right? This is the simplest model that we would ever entertain for longitudinal data, in which we have random intercept variance at level 2, intercept differences across people, and we have level 1 residual variance differences within persons over time. By the way, those are homework questions that are purposefully written that way. Between persons over time does not work, and within persons on average does not work. It's between persons on average or within persons over time. So at this point, I would talk about intercept differences as mean differences between people, because there's nothing to condition this on. There's no time zero or anything yet. So this would just be like just these sorts of differences. So let's say that I fit a fixed effective time, and I am intending this to be like Venn diagrams where the squares are like eating that pile of variance, kind of like a Pac-Man sort of situation here. So level 1 time is a time predictor, time level predictor, therefore it should explain time level variance. So we can talk about how much of the level 1 residual variance was explained by average change over time. Cool beans. Then we split. So note the pile was bigger, now it's smaller. Look, I'm a graphic artist. In addition to being a psychologist. So I took what was within person E variance, and I split it out into its new pile. So E is why are you off your line? Well, maybe you're off your line because the line that we drew for everybody doesn't fit you. You need your own. So part of that E variance, I would not say is explained. I would say it is reallocated. And this may be a semantic distinction, but to me it's not. Because this new pile of variance now represents another source of individual specific error. Reasons why people change differently that we don't know about yet. So it's still error, it's just not level 1 error. It's now a new kind of level 2 error. So I would call this a random linear time model. Now let's say that I think there may be bendy change, nonlinear change, and I add in time squared. Well, that should explain the part of the E variance that is still down here. E is why are you off your line? Well, maybe you need a bendy line, not a straight line. Seems reasonable. We talk about how much of the E variance was reduced by time squared as a fixed effect. Then we can take that E variance and split it out even further into random quadratic time slope variance as a third way that people differ from each other. So at this point, we have 3 reasons why people differ from each other, which then in turn would motivate a level 2 predictor for each of these reasons, as well as remaining, why are you off your line today? Everybody has their own bendy line, and that's still not going to be perfect, as long as you have at least 4 occasions. So this is a random quadratic time model. This could be a new baseline by which to introduce level 2 predictors. Okay, with me so far? All right. Here's the interactive portion of the program. I got my boxes. You got to tell me where they go. Why are you laughing at me? You're grimacing. So this is like a trauma response? That's what I'm getting here? The nervous giggles? Okay, so I'm trying to help, by the way. So this box says level 2 ed and then in parentheses by intercept to tell you what it's for. So where do I put this box? Which variance pile is this box going to eat? Yep, that one. Very good. How about level 2 group by intercept? Yeah, that one. How about level 2 ed by level 1 time? I've got 2 that are left unattended. Which one is it going to go on? Time or time squared? Time. And how do I know that? Because time is here and it's not squared. Now, I'm not trying to be annoying, but that is exactly my point. Like, that cross-level interaction explains the random slope of the predictor that's in the interaction, specifically. It has a very specific job to do in these models. For the same reason, level 2 group by level 1 time would explain the time slope variance. Then if I get to level 2 ed by level 1 time squared, it goes on the time squared pile. So this is what the scenario that we've looked at up to this point, where everything is nice and neat and tidy. Now the real world. Actually, no, a little more neat and tidy, just of a higher level of complexity. Real world, not quite yet. How about an education of group by ed? Yep, so this is a new type of level 2 fixed effect. Bladimir said that we know 2 and that there's 2 more coming. This is one of them. I would call this a level 2 interaction because it is amongst 2 level 2 variables. And it does not have any level 1 variables as part of it. Therefore, the only thing it can explain is the intercept. What about group by ed by time? Yeah, that one. And group by ed by time squared? 4-way interaction. We're going to do one of those in our example, I think. Maybe not. I think I took it easy on you and didn't do that one for the quadratic model, but it is possible. So this would be like the amount of bendiness that your line shows is moderated by both group and ed. So the extent of group impact on bendiness depends on your ed and vice versa. Something along those lines. Okay. How are we doing so far? Question?
So, with interactions, we can say the vice versa, right? So, like, if one thing is conditional on one, like, if A is conditional on B, then B is also conditional on A, right?
In this context, yes.
Does it impact the level 2 random intercept variance? Because, like, time squared is part of that, so it would affect group. Do you see where I'm going?
Not quite. Let me answer a question you may have asked, and you can tell me if that's not the question you asked. So the intercept is specific to time 0 because of the fixed effects of time and time squared in terms of its variance. So its intercept differences at time 0 is what this circle represents. It is not intercept differences that have anything to do with group or ed, because those are predicting those differences. Now, where I thought you might be going is talking about these interaction terms. So for instance, group by ed, I can talk about as how the effect of education at time 0 depends on which group you're in. I can talk about it as how the effect of group at time 0 depends on how educated you are. For these time interactions, I could talk about how the effect of education on change depends on which group you're in. I can talk about how the effect of group on change depends on how educated you are, or I can talk about how group differences over time narrow or widen as a function of there's a lot of ways you can talk about it. How the effect of group by ed changes over time is another way. So like if groups get closer together over time, for instance, like you could think of like racial inequality or something like that, hopefully that narrows over time. But if the extent to which that happens is only in people with lower education or higher education, that's your three-way interaction. And then this one would imply that narrowing does not happen in a constant pattern. It slows up or speeds down. That's where we're at. I'm Homer Simpson forgetting how to say the word fork at some point. It slows up or speeds down across time. Okay, did that answer any of the question?
I think you answered both my questions because I gave you a smushed question.
A smushed question.
So,
Yeah, this is not easy stuff. I will reiterate that. But this is the relatively neater and tidier case. Now, what about the systematically varying ones? Let's say that we tested our random quadratic time slope, didn't need one. So there's no circle out here. Okay? What are ed and group by intercept going to do? Yep, they're still going to go here. How about ed by time and group by time? Where are they going to go? There we go. We're running out of room here. Now, where are these guys going to go? Oh, yeah, they're like, wait, there's nothing here. What am I going to do? I got to go back to where this would have come from. Over here. Systematically varying effects are those that do not have a corresponding random slope variance. Time squared, that slope does not vary across people. So the only thing left for a systematically varying effect to explain is residual variance. So this breaks the earlier rule. Level 2 predictors can explain level 1 variance if they are part of an interaction with a level 1 predictor. And that level 1 predictor does not have a random slope. This is where the quadratic variance, slope variance would have come out of. It's still in there. It's just like a tiny little bit of it. So if there are no individual differences in the quadratic time slope, this is not going to go well. It doesn't necessarily stop you from trying. So that is my long-winded way of getting to this slide. Here are the rules as specified. So level 2 predictors by themselves as main effects reduce random intercept variance. Level 2 predictors that are part of level 2 interactions, like group by ed, reduce intercept variance. Cross-level interactions, they reduce either random slope variance if it's there for that level 1 predictor, or residual variance if it's not. And in practice, these variance estimates sort of shift around as you add things, and this does not always work out as cleanly as this slide implies. But this is theoretically what should happen. And we got,
When you say
yes.
if it's there, do you mean like if the random effect was significant?
Yes, and that's the problem. If it's there is an idea. How we evaluate if it's there currently is based on likelihood ratio tests. But just like any other significance test, it's a function of power. So if it's there is harder to determine in smaller samples of persons, or if there's less signal.
if we can detect it
Yes. If it's there enough, maybe, would be a better way to put it. If it's there enough to show up as a signal, then the cross-level interaction explains the corresponding random slope that goes with that level 1 predictor. If that level 1 predictor does not have a random slope, the cross-level interaction explains the residual at level 1 instead. So, a few slides about our squares and stuff. So I have links here, and on your reading list are a couple of papers by some folks who've been working on this problem for several years. I will point out that while I very much like the way they've clarified all of the different pseudo R-square measures that there are in the literature, because there's like dozens, literally. People keep reinventing the same things and giving them different names. They don't have a category for explained slope variance as a thing. In their version of this, they count random slope variance as having explained the residual. And I will forever die on that hill. That's just not right. But reasonable people disagree. So when you are describing effect size calculations using any kind of R-square, my advice would be to give the formula and a reference for exactly what you mean by that R-square, because there's too many kinds. And there's also a lot of really crappy simulation research showing that, like, hey, this R-squared doesn't work because when I add this predictor, it doesn't change. But it's like, no, it's supposed to not change because that's a level 1 predictor and this is a level 2 variance. Like, duh. That's not a very constructive thing to write in a review. Try to be nicer than that, but there's a lot of research that has that sort of tone to it. Because each of these R-square measures is targeting a different pile of variance or set of variances. And so they may not reflect changes if the predictors included do not work at that level. Okay. Other questions for now? Yes.
So in the clustered class, the cross-level interactions, did it also explain or like go towards that level 1? Okay.
Yep.
Okay.
Yeah.
Because there's not a random. Is there a random?
You can. So the question was, if we're in a clustered context, which I will be a year from now, if you have people nested in clusters, so students in schools or that kind of thing, yeah. So if you have a student level predictor in that case of some kind of student outcome, the extent to which, let's say, student characteristics predict their achievement, that may vary depending on what school they go to. If you put in a school level predictor as a moderator of that relationship, you would explain that random slope variance, the same as what I'm talking about, just with student whatever as opposed to time whatever. The rules are exactly the same. Okay, so with the 2 minutes we have left, tell me what you learned today. Actually, we have 4 minutes left, but I tend to talk a lot.
Time invariant predictors help us explain the variance that is partitioned into between persons and within persons, so level 1 and level 2. And if there is no random effect, you might still find a systematically varying effect, in which case the cross-level interaction is is describing some of the variance at level 1.
Yes, time invariant predictors are designed to account for variance at level 2. But if you don't have it, then they got to go back down and account for it at level 1 if you're fitting cross-level interactions. Yes, I would agree with that. And systematically varying means not everybody gets the same, not everybody gets their own, but people get different ones deterministically as a function of a level 2 moderator, but not otherwise. Those are the main ideas. And does multi-level modeling handle missing data? No. Incomplete rows are deleted, the end. That's the other thing. If you want to handle it or fix it, we need to move to a multivariate framework in which we can pretend that the predictors are outcomes. Then we can have missingness as long as we're willing to put on distributional assumptions to go with it. Anything I'm forgetting? And main effects do this. Interactions with time do this. How's that? Fair. Okay. All right then. So you can be working on your last formative assessment. I will let you know when your homework is up for the last one of those as well. All right? All right. Thanks for being here. Hang in there. We are all almost there. Hope to see you again on Thursday. Let us know if you need anything. Deal? Deal. Bye, Zoomers.